students, we have been discussing about ternary eutectic solidification behavior of ternary eutectic alloys, and I just told you that for a simple system in which there is no terminal solution, the solidification is very easy to follow. So, today we are going to discuss about the phase diagram in which the terminal solutions do exist, and I told you that I am going to scan the pictures from the book of Alan Prince and show you and discuss you here. But before that, let me just take a recap. In a ternary eutectic with no terminal solution, the phase diagram will look like very simple like this. Okay, you can clearly see here there are 3 deep eutectics on the 3 binary sides, and finally they lead to a ternary eutectic at the center. If I project it onto the Gibbs triangle, they look like this. The 3 eutectics are marked by these red arrows. The central one is the ternary eutectic, which is sitting inside the triangle. Now, one can easily see how the solidification will happen just by knowing the 3 dimensional space model, as well also by using the projections on the Gibbs triangle. In a 3 dimensional space model, as you can see here, if I have any composition, alloy compositions which is sitting suppose on the primary phase field of A, this corresponds to here the composition here. So, very easy to follow solidification. How we are going to do it? I showed you that we can first join these points, because this is sitting inside the primary phase field of A with the point corner A, and if I join this like this, then I extend this line further. So, if I extend this line, that means what? From this point, as the alloy is getting cooled down, you are going to have more and more precipitation or crystallization of A. Finally, the crystallization A will continue till this red line here is meeting the curve on E2, right, this curve. So, as it meets here, you are going to have crystallization of both A as well as B coming from the liquid, and finally, the solidification path is follow along this path. So, therefore, this is going to be like this. Okay. Similarly, any other cases we can discuss, but in a ternary eutectic system, there are different set of alloys which can undergo eutectic reactions. Obviously, the most important alloy is having a composition corresponding to point E, and this alloy with corresponding to composition E will undergo ternary eutectic reaction, which is nothing but liquid going to alpha plus beta plus gamma. There are other alloys also which can undergo this reaction. I want to give you some examples. One is this one which I have given. So, alloys which is sitting compositions which are falling on the primary phase fields of A, B or C will start crystallizing the component which is in which phase field it is sitting, and then finally, it will lead to formation of the binary A plus B or B plus C or C plus eutectic, and at the end you will have ternary eutectic A plus B plus C. This is the category number 2. So, category number 1 was composition corresponding to point E, category number 2 is composition which is falling in the primary phase field. Category number 3 is the composition which are falling on these 3 eutectic points, okay, binary eutectic these 3 falling on these 3 curves actually E2E, E3E or E1E. As you can see, if the composition falls on these 3 curves, each of one of these 3 curves, what will happen? First, it will crystallize both 2 components A and B in case of E2, B and C in case of E3, and C and A in case of E1, right. And this will keep on crystallizing in to these 2 components or these 2 phases, rather A and B in case of binary A, B, E2, and B and C in case of E3, and C and A in case of E1, and finally, it will reach the point E where ternary eutectic will form. Okay. So, there are 3 sets of alloy compositions which you have seen. All these alloy compositions will lead to formation of ternary eutectic, but obviously there are other things will happen prior to the ternary eutectic reactions. In the first case, there will be nothing else, if the composition is falling on the point E, then only ternary eutectic will form. In the second case, first A or B or C, any of these three components crystallize, followed by crystallization of the two components together, like A and B or B and C or C and A, depending on which binary, which points it is meeting, either E2E, E3E or E1E, right. And finally, it will be liquid will be final liquid will solidify as a ternary eutectic. A third case, from the beginning onwards, the liquid cooling of the liquid will lead to crystallization of both two phases, A or B in case of B2 and B or C, B and C in case of B3 and C and A in case of E1. So, these are the three important crystallization events I told you, pathways. And okay, now let us look at the crystallization of the solidification of the alloys for a eutectic system, for a ternary eutectic system in which you have terminal solutions like alpha, beta, beta is this side and gamma is present, okay. Beta is here, gamma is here present. In this case, there are actually 4 set of alloys which can undergo ternary eutectic reaction. Obviously, the first one is alloy composition corresponding to point capital E, and this will lead to formation of only ternary eutectic between alpha plus beta plus gamma. That is easy to understand. Second one is alloy composition lying on the invariant monovariant rather liquid curves like E1, E1E, E1 is this curve, you can see red mark given, okay, or E2, E3E or E2E, right. In all these things, what will happen? First thing it will form is, it will crystallize both alpha plus beta. Suppose if I take alloy composition corresponding to this curve E1E, so as the alloy composition hits, as the cooling down, it will hit this surface. So, this will crystallize both alpha and beta, finally it will reach L2, from L2 it will move to E, capital E, where it will crystallize both alpha plus beta, all the things say alpha plus beta plus gamma, correct. So, this is the okay. So, let me write down the first composition is corresponding to E, second composition is corresponding to alloy composition lying on the monovariant curve E1E or E2E or E3E, okay. Any of these monovariant curves on which the composition lie. Third one is that tuff. If the composition lies on the tuff of AE, AE is what? A corresponding to this, E corresponding to this. So, this is the tuff, okay. You create a tuff here. So, the one which I have shown is basically the one which is lying on that, okay. So, AE tuff or BE or CE, right. And fourth one is basically composition lying on ABE or BCE or ACE, the 3, any of these. So, there are 4 different compositions which are important, but the top 2 I have already discussed. Let us now discuss the 3. Okay, so, one such composition is shown as a X. Now, as you see here, follow everything which is shown as like a red arrows, then it will be easy for you to understand. If you see here carefully, as I cool it down the alloy, things will start happening at point L1. Why? At L1, this alloy composition will touch the liquidous surface which is going down, this liquidous surface is going down, right, liquid surface which is going down, it will touch there, and therefore, it will start crystallizing alpha of our composition alpha 1, you can see here, correct. So, as it crystallizes alpha of alpha 1 compositions, the and further cooling will lead to change of liquid composition along L1 to L2, correct, and similarly solid composition will vary along alpha 1 to alpha 2. What will happen from cooling down from L1 to L2, or rather temperature T1 corresponding to L1 to temperature T2 corresponding to L2 is nothing but crystallization of more and more alpha, and alpha will have different compositions along these curves like alpha 1 to alpha 2, but as soon as I reach L2, this is hitting the curve or hitting the trace of U1E, right. You can see here this L1 L2 line or curve is meeting the trough or the valley rather U1 small u1 to capital E. Because it hits that valley, this means that it has to crystallize both alpha and beta. So, that is why I have drawn a triangle with compositions of alpha given by alpha 2, composition of beta given by alpha 2 beta 2 and the liquid L2, correct. So, this is 3 phase equilibria between alpha 2, beta 2 and L2. So, because you are continuously cooling down, so therefore, from L2 to above E, this will keep on crystallizing alpha and beta of different concentration, and the constant composition of alpha will vary from alpha 2 to capital small a, beta will vary from beta 2 to small b, correct. These two things are shown here. I hope you are following it. And finally, once the composition is meeting at the 4 phase equilibrium point E, then the remaining liquid is solidified as a ternary eutectic, correct. So, therefore, it is not very difficult for you to follow it up. Let me first reiterate again. So, as I cool down the alloy from the high temperature, nothing will happen above the point corresponding to L1, and as it comes down to point L1, this is going to meet the liquidous surface, and because of that any drop in temperature further below L1 will lead to crystallization of alpha of composition alpha 1, correct, and this one will continue, this crystallization of alpha will continue till as the temperature goes down from T1 to T2 corresponding to point L2, and liquid composition will change from L1 to L2, whereas solid composition of alpha will change from alpha 1 to alpha 2. Now, something new happens at point L2. Why? Because L2 is a point corresponding to which is sitting on the valley small u1 capital E, this valley small u1 capital E. Okay. This is the thing, let me write down again, it is sitting on that. So, because it is sitting on this has to crystallize both alpha and beta, because this is the eutectic, u1 is a eutectic corresponding to binary of AB producing alpha plus beta. So, therefore, the valley connecting u1 to E will produce both or lead to crystallization of both alpha and beta, and here same thing will happen, alpha 2 of alpha composition corresponding to alpha 2 and beta composition beta 2 will crystallize from liquid. So, that means that you are going to have a 3 phase equilibria between alpha 2, beta 2 and the liquid L2. You form a triangle, and any 3 phase equilibria is represented by a triangle we have seen, right. So, further cooling from L2 above E capital E lead to nothing but crystallization of more alpha and beta. Once it reaches the point E, this is going to crystallize or produce ternary eutectic. This is what will happen. Okay. Now, if you are having a compositions like sitting on ABE, right, ABE on this, okay, or BCE, you can say BCE or ACE, does not matter. Okay. Here it is showing ABE, what will happen? This will lead to formation of again alpha and beta simultaneously, followed by formation of ternary eutectic. So, there is no need of discussing that. Now, further to this we can also have different variation of ternary eutectic, right. So, in this case we have shown all the binaries AB, BC and CA, they form eutectic among themselves, but that need not be the case. I do not know whether I have told you that this is the unique ternary system, but that is not 100% correct. So, there are situations where even ternary eutectic is possible or 4 phase equilibria of ternary eutectic type is possible even when some of the binaries are not forming eutectics. Okay, let us see what will happen. I will just give you 2 examples of that on the board, and let us see whether we can draw it properly. One is that when 2 binaries are eutectic, 2 binaries form eutectic and 1 plus 1 binary forms peritectic. So, how it will look like? Let us draw it, although it will be little complex, but still follow me, you will be able to understand it very clearly. So, suppose I have AC binary as an eutectic. I have drawn using white color AC binary eutectic, and then also BC binary forms an eutectic. Okay. But on the other hand, AB forms an peritectic reaction. AB couple forms an peritectic type of phase diagram. So, how it will look like? Not very difficult to do it. We know that peritectic reaction will be like this. Let me just distort a little bit, so that you can understand. So, you see here there are two eutectic reactions, E3 and E2, and there is a peritectic reaction Pu1 here. So, and if I try to connect them using this color chalks, if I try to connect them, this will form a primary eutectic alloy. So, let me see whether I can do it. This is a green color chalk, this is 0.1 and this one another point. So, connect these two and these two eutectic, these two eutectic, or rather let me draw the triangle this way. So, this is eutectic, this is alpha beta. So, this also forms a ternary eutectic. So, this is one variation of the things. Second variation, that you can have two eutectic. So, this is one variation number 1. Variation number 2 is two binaries form eutectic and one binary forms isomorphous. This can also lead to ternary eutectic, and it is little bit, I will draw very simple way, it is not complicate things. So, first is that the binary between A and C forming the first eutectic you can see here, and the second eutectic is between A and B. This is also done, very clearly seen, and the third one will form an isomorphous. Okay. So, let me just draw this isomorphous between P and C. This will also lead to an ternary eutectic inside it. Okay, it is not very difficult to understand that. So, you can actually connect these two eutectics and one of these ends will lead to a eutectic, that is all. So, there are different variation. There is another variation also. You can have, I am not drawing. The third variation is very subtle also. I am not going to draw it, because for you to remember is you can one binary eutectic plus two binaries form peritectic. This will also lead to formation of a ternary eutectic. So, you have seen that a two ternary eutectic where all the three binaries forms eutectic, and that we have discussed extensively in details, and there are other two in other variation of that is that in the first case two binaries form eutectic or one binary form peritectic, or one binary form eutectic and two binaries form peritectic, or third case or the second case here two binaries form eutectic, one binary form isomorphous. All of these will lead to formation of isomorphous ternary eutectic inside the triangle, correct. So, with this I conclude the section on these ternary eutectic systems. Now, in the next lecture briefly I am going to tell you other two phase equilibria. Okay.